This is section 2.3. We're going to talk about Venn diagrams and set operations. The universal set is a general set that contains all elements under discussion. There's a guy named John Venn. He created what we call Venn diagrams to show visual relationships among sets. With a Venn diagram, the universal set is represented by a rectangle. That would be this right here. Subsets within the universal set are usually depicted by circles. So in this case we have set A, that's a circle. Sometimes ovals, sometimes other shapes, but in this class we're going to use a circle to represent a set within the universal set. Use the Venn diagram to determine each of the following sets. So the universal set, that's anything inside the rectangle. Okay, so anything inside the rectangle, we have the $, the M, and the 5. $, M, and 5. But make sure when you do the universal set, you also include what's inside set A. So we also have the square and the triangle. As far as set A, the only thing that's inside set A would be the square and the triangle. For C, we want the set of elements that are in U that are not in A. So that's anything outside of the circle A, and that would be the $, M, and the number 5. Disjoint sets, those are two sets that have no elements in common. For a Venn diagram, they would look like a circle, two circles, completely separate, no overlap. Equal sets. Remember, equal sets is where one set is exactly the same as B. Another way of saying is A is a subset of B and B is a subset of A. It's just the same way of saying the same thing. And when two sets are equal, we just draw one circle and we put the A equals B. Proper subset. Remember, proper subset is any subset as long as they're not equal. So all elements of A are elements of B, but not the other way around. So we've got the B and we've got the A inside. Most of the time when we talk about Venn diagrams, we have something like this picture right here. Some elements in common. Some means at least one. So if we had 0 items in common, we would have this picture right here. So we have to have at least one item in common. That means there's something here. We don't know what it is necessarily, but we know that it has to have at least one thing in set A and in set B at the same time. Use the Venn diagram to figure out what is the universal set. Universal set. Now when we're looking at this picture, I know it's kind of confusing, but these Roman numerals are not in the set. They're just labeling the region. So you can ignore the Roman numerals. Okay, so we need to figure out the universal set. That would be everything inside the rectangle. So we have A, B, C, D, E, F, and G in the universal set. For set B, we're looking for anything that's inside the circle B. Be careful to include D. D is also inside that circle. So for set B, we have D and E. The set of elements in A but not in B. So this time we don't want the overlap. So in A but not B, so we have A, B, and C. In the universal set that are not in B, be careful again, it is possible to be in set A. So in the universal set but not B, so that would be anything that's outside of B. So anything that's outside of B, we have A, B, and C are not in B, and F and G are also not in B. The set of elements that are in both A and B, D is in A, D is also in B, so the only thing that they have in common is D. The complement of a set, we use this symbol, it's a little apostrophe, is the set of all elements in the universal set that are not in set A. If we want to use set builder notation, we would say A complement is equal to the set of all X such that X is an element of the universal set and X is not an element of A. With a Venn diagram, the shaded region represents the complement of A. So this part right here, anything that's outside of A. Suppose the universal set is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And A is 1, 3, 4, and 7. We want to find the complement. So we could ignore 1, 3, 4, and 7. 1, 3, 4, and 7. We want anything that's outside of 1, 3, 4, and 7. So the complement, A with a little apostrophe, would be anything that's left over. So we have 2, 5, 6, 8, and 9. And in a Venn diagram, that would be this stuff right there. The intersection of sets A and B, we use this symbol right here. Okay, looks like an upside down U, is a set of elements common to both. Set builder notation, A intersect B is equal to the set of all X such that X is an element of A and X is an element of B. With an intersection, it's always going to be an AND. The union of two sets, we use this symbol, looks like a U, is a set of all elements that are in A, or in B, or in both. Set builder notation, A union B is equal to the set of all X such that X is an element of A, or X is an element of B. For any set, the intersection with the empty set is going to be empty. The union with the empty set is going to be the original set. I'm going to stop here for the end of part 1.